Good morning, everyone. My name is Sean Kunisaki, and I'm the current chair of the APSA Research Committee. It is really my distinct honor to introduce our next speaker, who's Dr. Lily Cheng, who was one of the 2022 Grosfeld Scholars and recipients of the award. For those of you who don't know, Dr. Cheng did her undergraduate at the UC San Diego, where she graduated Phi Beta Kappa and then completed medical school at UC Davis. From 2012 to 2019, she was a general surgery resident at UCSF. And during that time, she won an SUS Research Award and took a 2-year hiatus to do basic science research under the tutelage of one of my mentors, Dr. Alan Goldstein at the Massachusetts General Hospital. She then completed her pediatric surgery fellowship at the Texas Children's Hospital in 2021 and is currently an assistant professor of surgery at the Baylor College of Medicine, really with a special interest in colorectal surgery. In September, Dr. Cheng will be moving to Charlottesville, Virginia, where she'll be taking on a faculty position at UVA Children's Hospital. I think a testament to how incredible Dr. Cheng is as a young investigator, as a young surgeon scientist, is really not only her ability to garner a Grosfeld grant, really in her first year of practice, which I think is quite impressive, but her ability to already become NIH funded, which she did actually last year, being awarded a KO8 award from the NIH. So without further ado, she's going to talk today about investigating the role of biomechanical forces in the enteric nervous system and Hirschsprung's disease. So let's welcome Dr. Cheng.
Thank you so much, Dr. Kunisaki, for that really kind introduction. And thank you for allowing me to speak today and to share some of the work that I was able to do with the help of this great award. So I think everybody here in the audience knows what Hirschsprung disease is. We know it affects 1 in 5,000 infants, and we know that it's caused by the absence of the enteric nervous system in the distal intestine. What we don't know about Hirschsprung disease is why, even after we do a technically perfect operation, bowel dysfunction still persists for many children. So this led me to question, if we remove the abnormal intestine, why do kids still suffer from dysmotility and enterocolitis? I think we've collectively started to realize now that the ganglionated intestine in Hirschsprung disease is not entirely normal, and I wanted to look further into this. My overarching hypothesis was that chronic forces of stretch and distension, both directly and indirectly, affect bowel function. First, through alterations in the enteric nervous system itself, and second, by changes in the surrounding extracellular matrix. So first, I'll share some things that we've discovered about the direct effect of force on the enteric nervous system. Using an in vitro system for cellular stretch, we subjected enteric neuronal stem cells isolated from adult mouse intestine to a supraphysiologic level of stretch. When phenotypically compared to cells grown without stretch, the stretched cells had a similar percentage of neurons and a similar rate of neuronal proliferation, but had notably shorter neurite branching. In order to find the mechanism for this, I wanted to look at the mechanoreceptor piezo-1 as a possible mechanism. I chose to look at piezo-1 because the piezo family of mechanoreceptors has been implicated as important for visceral sensation in other organs. For example, a knockout of piezo-2 in the bladder causes megacystitis and dysfunctional voiding. So I hypothesized that piezo-1 might play a similar role in the bowel, because in my preliminary work, I had found that piezo-1 was widely expressed in enteric ganglia. These are some recent images from RNAscope showing expression for piezo-1, piezo-2, and TUJ1, which is a pan-neuronal marker. And it shows co-localization of TUJ1 and piezo-1 in the enteric ganglia. In my preliminary work, I had also interestingly found that piezo-1 seemed to have diminished expression in the ganglionic portion of Hirschsprung disease, as demonstrated here with immunofluorescence. In vitro, we found that ENS cells grown in the presence of a piezo-1 agonist, YOTA1, exhibited a similar phenotype of shorter neurite length, similar to ENS cells grown under stretch. They also had no difference in the percentage of neurons or the rate of proliferation when compared to control. In addition to shorter neurite length, piezo-1 agonism also seemed to inhibit the migration of ENS cells in vitro. Neuron migration from neurosphere center was measured in the presence of piezo-1 gain and loss of function, and was significantly less with the piezo-1 agonist, YOTA1, and was significantly greater with the piezo-1 antagonist, GSMTX4. That one doesn't have a cool name. Further, Chioma is going to be a resident at, or is a resident at UVA, who's going to be working with me in the coming year. She's previously worked on the ENS, so I'm really excited to be working with her on characterizing this effect of piezo-1 gain and loss of function on ENS cells further. Meanwhile, this past year, as another way of looking at the role of piezo in ENS, Yinka Olatoye, who's currently a research resident in the lab at TCH and is working with my mentor, Dr. Kaswani, applied his knowledge of wound healing from his work with my mentor to look at neuronal recovery after injury. I'm going to play this video here. I don't know how well it's going to project, but what it shows is that a scratch wound is being made on ENS cells in culture. So what Yinka did was plated cells for 7 days to let the neurons reach a state of confluence. Then he created a scratch wound, and over the following 7 days, he measured how well neurons grew to fill in the wound. And in the presence of piezo-1 agonist YOTA1, there was significantly decreased recovery for neuronal injury. We're continuing to investigate the role of piezo-1 in the ENS, specifically the potential differences in Hirschsprung disease. But I want to make note that very recently in the literature, piezo-1 has also been tied to force-related inflammation and fibrosis in other organ systems, which actually ties it nicely to my next aim that focuses on the relationship between force, the extracellular matrix, and the relationship of that with the enteric nervous system. I think most surgeons who've operated on Hirschsprung disease have noticed that the proximal bowel may sometimes be thickened and stiff. Using atomic force microscopy, we've actually been able to measure the stiffness of the muscularis propria in a mouse model of Hirschsprung disease compared to wild type. And we found that actually the proximal ganglionic colon in Hirschsprung mice was much stiffer than the equivalent section of wild type colon. Brittany Sue's a sophomore at Rice University, and she did some work with me last summer. She compared Hirschsprung to wild-type colon using trichrome staining and showed that the proximal ganglionic Hirschsprung colon was significantly more fibrotic, which may be one reason it's stiffer. Brittany also performed PCR and found that several ECM-related genes were differentially expressed in the proximal ganglionic Hirschsprung colon compared to the wild-type littermates. The expression in the proximal ganglionic colon was actually similar to the distal aganglionic colon, suggesting that though the proximal colon in Hirschsprung may have enteric ganglia, other attributes of that colon may still be abnormal that we don't recognize yet. We don't know if these differences that we found in the proximal Hirschsprung colon are actually just inherent in Hirschsprung disease as kind of an unrecognized transition zone, or if they might be the result of chronic stretch and dilation. But as evidence to the latter, we do see that the extracellular matrix is dysregulated when the gut is stretched. Yinka and Walker Short, who was a resident in the lab last year and who will be in the match this coming year, looked at differential gene expression in stretched and unstretched wild-type mouse colon. And they found that several ECM-related genes, namely collagen, matrix metalloproteinases, and laminins, were significantly different in the stretched colon. Looking at 3 different models of bowel distension in mice and in humans, Yinka and Walker also found that the distended bowel had increased fibrosis in all 3 of these models. Yinka's also taken this one step further and looked at pathology specimens from bowel resections performed in patients with chronic constipation and found that about a quarter of these patients also had notable fibrosis in the distended colon that was resected. To tie this all back to the enteric nervous system, we're now actively looking at how stiffness in turn affects ENS cell growth. One of our collaborators has conveniently already studied this in central nervous system neurons and found that stiffer substrates inhibit neuronal migration and neurite extension, very similar to what we've already seen with piezo-1 agonism and stretch. So we're very eager to see what the effect of stiffness is on ENS and the pathway that might be involved in that. So future directions. I think we've seen some really exciting results just in this past year. In the next phase of this work, I'd like to focus on looking at neuronal phenotype in more detail, but also looking at neuronal function in the conditions of stretch and stiffness. And we're testing not just piezo-1 as a possible mechanism, but also using transcriptomics to take an unbiased approach to uncover the whole pathway by which enteric neurons sense force. And finally, with the help of my partner, Dr. Christy Rylon, we've biobanked now close to 30 human samples, about half from patients with Hirschsprung disease and half from controls. And so ultimately, we're looking to correlate some of our interesting animal data with patient samples and real-life clinical outcomes. So as Jessica Kandel said, I can't do this without my mentors, Dr. Kiswani and Dr. Goldstein, the team of people who've helped me with this, and especially the ABSA Foundation for their generous support.
Any questions for Dr. Chen?
James Dunn from Stanford. Great work. As you know, our lab is interested in making the intestines longer by applying the force, and we have seen some of the things that you have seen in terms of the effect on the ENS. We've also seen that when the force is taken away, things reverse. I wonder if you have any evidence of that in the models that you've looked at when the things have changed and then you take away the force.
Yeah, thank you for the question, Dr. Jen, and thank you for your collaboration also and your support. I think it's always reassuring that we've come to similar conclusions in parallel, that we were on the right track. I think some of the work that Yinka did using the in vitro system, the scratch wound test, might help us find the pathway by which the enteric nervous system recovers to injury, such as stretch. I think we haven't tested what mechanism is behind that yet, but I think that is a good system to investigate that. I know that at DDW earlier in the week, there was some data presented on possible neuronal transdifferentiation from glial cells or precursor cells, Schwann cells. So I think that's still an area that's pretty hotly under investigation in the enteric nervous system.
Other questions? Dr. Cheng, I had one question for you. One of the phenomena we sometimes see clinically is that when stretch is relieved, for example, when children have their bowel diverted, some of the physical changes that we observe regress. And I'm wondering how that might read out in terms of the molecular exploration that you've been pursuing.
Yeah, I would love to know the answer to that question, and we're still working on that. I think Hirschsprung is one good model. I think another model that we're kind of in parallel investigating is chronic constipation, which is far more common, maybe not as sexy to investigate, but I think answer would be a good model to pose some of these questions.
We have one more question.
Hi, Lorraine Kelly-Kwan from CHLA. This is really very compelling work. I'm interested to hear how you think your findings are going to ultimately be translated to therapeutic interventions for our patients.
Yeah, I think that the goal is to understand the reason for the dysfunction better, and if we can identify some small molecule, maybe it's piezo-1, maybe it's something else, where we could potentially have a pharmaceutical intervention that might be some supplement to surgery in Hirschsprung disease or in chronic idiopathic constipation.
Thank you very much.
Thank you.